I want to give a computer demo next that's going to show exactly what this DTFT looks like and how to calculate it explicitly in MATLAB. This will bring together a lot of ideas. Good. All right. So we want to graph. The goal is to graph the DTFT. We've already found what the DTFT is by hand using in the example with those summations, and now we want to graph it. And in words, I'm going to try to just to say what it is so we don't forget it. It's 3 over, we've got this 1 minus 0.5 times the exponent of minus j omega. And all of that is in the denominator. So this was what our DTFT is. We want to figure out what it looks like. So we're going to start out by, it's a function of omega. So we're going to start out by creating an omega. And I'll linspace that. Although it's unique between 0 and pi, I'm going to graph it between 0 and 2 times pi, just so you can see that kind of that folding mirrored relationship we talked about earlier. And it doesn't matter how many points we have. MATLAB will figure it out all instantaneously, so I'll give it a bunch of points. Here's our DTFT. So x is equal to, from the top, 3, and we need to use a dot divided because we're doing a vector, 1 minus 0.5 times the exponent of minus j dot times omega. Definitely want to put that semicolon after it so it doesn't spit all those results. Quick check, our x is 1000 and our x is complex. We can't simply plot omega versus x because x is complex. So we're going to have to plot it versus its magnitude. And that we can do. And let me show you what that looks like. So that's what it looks like in the frequency domain. So sure enough, between 0 and pi here, I'm sorry, yes, between 0 and pi, it's unique. You can see it has a lot of low frequency energy. And that makes sense because remember, our time domain waveform didn't oscillate up and down. It just simply decayed away. So it's got some low frequency energy, no high frequency energy. And then you can see how it's symmetric around pi, both going up and symmetric around 0 on the left-hand side. If you wanted to graph its angle, you could do that. And this is now graphing its angle versus x. Something that might make it clear about where our pi's are is, let's go back to its absolute value, is you could take omega and divide it by pi. And now these units are in units of pi. So this is 1 pi, and this is 2 pi, and this is 0. And that's kind of a little clearer about what you're seeing. Similarly, if you wanted to look at its angle, you could divide its angle also by pi. And now you can see that this is at 0 point, this is at pi, this is at 2 pi on the horizontal axis. Its vertical amount is the angle of its DTFT, and you can see it never comes close to a full pi, so it doesn't want to wrap around. If it did look like it wrapped around, if all of a sudden you see it suddenly changing from +1 to -1, you could always unwrap it. You could do something like this. Unwrap your angle. Here it obviously doesn't do anything. And if you prefer to have your angle shown in degrees, you could just simply multiply that by 180 over pi. And now you can see what your angle is in degrees.